Okay, let's pick up where we have left off. I'm sharing the screen, right? So last time we didn't talk about this open boundary conditions. So here we are trying to find analytically the open boundary conditions for this 1D 1D model world. Okay, we have a left boundary, which is this discrete point, and then the right boundary, which is this discrete point. So the trick here is to transform the original equations, the momentum equations, and also the this is continuity. Okay, the two equations into an uncoupled version. So how do we do that? Boundary conditions for okay. So first of all, we have the two uncoupled equations. We are using the mean wind speed, the mean wind as the advection. Okay, and then the height of the water surface or the fluid surface. Also the advection, convergence or divergence term. Okay, and then we can, so here, they are the they are coupled. What does it mean by that? What does it mean by coupled? So for the momentum equations, you will also have the height here. So the two variables are coupled. For the equation for the height here, you have u, right? So the goal here is to convert these two equations so that only one equation only contains one dependent variable, or you can only see one dependent variable. Okay, so we turn this into a nicer form first. So we use big U instead of U bar to simplify the situation. And okay. Okay, here C equals 2, which is the speed of gravity waves. Okay, and we write these two. In the matrix form. Okay, 有冇人明啊？有冇人記得 matrix form 係點㗎？ Okay, you're all senior students. I don't think you would forget this, right? So this looks very familiar because this is the same form as the affection equation. Right? This is this one. And A is here. Okay. Okay, then the next part is kind of optional. No, it's optional. So how do we turn the original shallow water equation into this decoupled? So they are decoupled form. Because if you look at this, okay, don't worry about the values of D and E first. So they are new variables, and you can see that the equation only contains D, and then the other equation you only see E. So they're decoupled. So how do we do that? First of all, we multiplied Q. So what is Q? Okay, Q here by this 2 by 2 matrix. Okay, so we do the multiplication. Okay, so there you see the new variables D and E, which are these two. Okay. Okay, next. Again, the same matrix, and then we find, this. Okay. 你哋記得點揾㗎係嘛？呢個 Anyone who needs me to go further? How we find this? Okay. Let's say if this is P, then it's pretty straightforward how to find this inverse. We do row operation. Okay. So at last you will get this, and then you will find it. So this is the inverse. So this is how we find this. So why do we find these two? It's for the next step. Okay, we multiplied the matrix A here, this one. By so after you have done this, it's no longer a anymore. We are actually symmetrizing the matrix. So why do we symmetrize the matrix? So if this matrix is symmetrized already, or symmetric matrix, so you have two zeros here. We do this to make it symmetric so that the equations are decoupled. Okay, and very mechanical operation here. So you know the values of A here, right? So this is A. OK， 按咗啦，總之最後咧都會OK, finally you'll get this one, the symmetric version of A. Okay. Okay, so now we write. Oh, this is not optional here. Now we rewrite this one. You know that you have two new variables, which is made up of all variables, of course. Okay, so this is what you can see on the slides here. So each of the decoupled equations is well posed. So if you want to say if this problem is well posed, it should be where these two conditions here, the boundary value is provided in the inflow or no value is specified at the outflow. Okay, so there are different situations depending on the value of U and C. Okay, so there are two situations here. The first one is the red one here, and the second one is the green one. Okay, so for the red one, C is smaller than U. So C is still gravity wave speed, and U is the speed of the affection. Okay, so both U minus C and U plus C, because U is larger than C, right? So we care about this because that might make your affection negative. Okay, so both of them are larger than 0. So which means that all the things are for the two equations, they are both coming from the left-hand side because they are both positive, right? Both coming from the left-hand side, and you have to specify the boundary value at the left-hand side because they are coming from the left-hand side, and you don't need to care about the outflow because when they reach the outflow, you will have the solution for that. Okay, so both D and E should be specified at x equals to 0 and none specified at x equals to L. Okay, so this is the first situation, and the second situation is that U is smaller than C. So now you have a problem. So U is smaller than C, then this one is negative, right? This one is negative, which means that you have the second situation here. For the u plus c, the equation where you have u plus c, you have to specify the boundary condition on the left-hand side. And for the other, for the variable which is affected by u minus c, then you need to specify at the other side, because things are coming in from the right-hand side, right? Because it's negative. Okay, so the two situations here. So now we need to care about, okay, this is, okay, maybe we don't go to the open boundary condition first. So here, in many geophysical applications, we know that u, or the magnitude of u, is smaller than c, which is the second situation in here, the green one in here. Okay, so we know that we need to specify the inflow for E on the left-hand side, and then specify the inflow for D on the right-hand side. Okay, and here this is just showing you the showing you the relationship between the two variables. So why do we do this? Because you need to know the weight or the ratio between the two values at the boundary. So, or their relative importance in the boundaries. So F is the forcing. So if you just look at this first equation, E could be expressed, because for D, this is the outflow, right? D is coming from the right-hand side. So D is the outflow. So somehow they are related by this value alpha 1. And we can express the two variables u and eta in the similar way. Okay, because if you substitute these back, then you know that which one you will need at the boundaries. Okay, and F is representing the external forcing. So this is less important comparing to the next slide. Don't worry about this. So this is just telling you the ratio between the boundary conditions of u and eta. So depending on the value of alpha 1. Okay, still the second situation from the last slide. We will not talk about the first situation because it's not applicable in the geophysical world. Okay. Okay, next we talk about the open boundary conditions for this one-way wave equation. So this is one-dimensional world. We have the affection model for the middle discrete points, but we don't have a very an elegant way to deal with the open boundary condition. So anything you substitute in here, constant or some equations you have tried last time, the different methods, there will be reflection. So I guess you have already tried to do the simulation, right? So whatever you do, you'll have reflections, and that's not good. Okay, and here we have an analytical way to deal with this for this very simple model. Okay, we have the decoupled equation. Okay, and E okay, so what does it look like in the model world? So if this is y-axis is t, so time goes upward in this graph. And x is this dimension. So if you, whatever signal you have, last time we have talked about this, right? It will go, so if we are only talking about E, because E is coming from the left-hand side. So, wow, dear. Okay, they will travel like this, right? So E is moving this way. And we know the slope for this. If this is X naught. Right? This is talking about E only. And we know that U is smaller than C, as in many geophysical situations or application. So the incoming D, so where would D be coming in? D would be coming in on the other side, right? D is coming this way. Oh, so sorry. Draw another graph for this. Again, the same graph, but for the other, for D, for D, what would that look like? Okay. Oh, D. So this location is L. And whatever you have. So this boundary here, if you have something, D has some values, then that would be a disaster because you know that the signal should not be coming from the boundary, right? You want the boundary condition to be, of course, you don't want anything coming in this way, right? So anything you have in the initial condition at this boundary, it will travel into your model like this. And you don't want that, right? You want the original, or at least the initial values here to be 0. Nothing is traveling like this graph. So if you have something, it will travel into your model. So here, D is traveling this way, right? Plus U minus C is zero. Okay, so if U minus C is less than 0, this would be the graph for D, describing the things happening. So you know that the incoming D at x equals to L, just as I said, here, x equals to L. Should be 0 for all time larger than 0. So you want this to be 0, not just the initial condition, for all to the eternity, okay, of time. And provided that if no incoming wave is expected at x equals to L. Okay. Hence, in the wedge shape meaning this wedge shape region, U equals to Y, because D should be 0, right? If this is 0, then U equals to this term, right? Okay, moving forward. Okay, so not hence. So you know that the outward E, so we are going back to E. So here, that's the answer. Okay, here, this location L. The outward E at x equals to L and near x. So the values here. We know the equation, right? So just put the values of E back to the so-called affection equation, right? And we substitute. So here is what we found from assuming there is no incoming wave on the right-hand side. And here is what we have for E. So we combine the two things that we know. Just substitute this, right? And okay, it's pretty straightforward. Radiation, you have already found the radiation condition, right? This is the radiation condition where, or open boundary condition where D is equal to 0. So we substitute them back for U. So the radiation condition, or the open boundary condition for U at x equals to L would be, because you substitute this back, so you turn this into U, right? And you turn this into U. So you just divided that by 2 and Okay, so we do this by making use of near L, which is here. Oh. Okay. So we have found this, and also similarly, we have found the other equation. Right? If you substitute this with this one, and then you substitute this with this one, then divided the whole equation by 2, then you get this similarly. Okay. So similarly, we can do the same for x equals to 0. E should not be going out on this side, right? Or should not be going in, sorry, on this side. Mathematically, we do this similarly. What does it mean? It means that if you want to avoid all the reflections in your 1D model in here, you will need to apply this to any variable. Then you will get 0. Okay, you will not get reflection or any. By reflection, we are talking about incoming signal, right? From this boundary. Also incoming signal from this boundary. We apply this. So this is what we found through all the steps in here, right? What we found in here, these two. If you apply the equation to U, then you will get open boundary condition. And if you apply the same equation to this variable, to this term, then you will get 0 reflection. Okay, and similarly for the left hand side, for the left hand boundary, you do the same. Only this time is U minus C. So this is how we find the analytical open boundary condition for the one-way wave equation. Okay. So next, what about time dependent? Boundary data. So if you have like a smaller or higher resolution regime, and then you have a lower resolution on the outside. So how do you deal with the boundary? Or this is too fancy. Okay. Just talk about the example we have. So you have smaller delta x and then larger delta x. So how do we deal with this, the boundary? You will need the constant input of the constant signal coming from the larger area, right? They are representing the outside world. So you need the signal coming in, right? You don't want open boundary condition in here anymore. So how do we do? And then you will need the input from the Crosser resolution constantly. Okay, it's not just the initial condition. You will need this every time step. So how do we deal with that? So now we allow changes in surrounding fluid to influence the interior solution. Okay, and assuming that we're using the same model, right? UE and eta E are U and eta in larger domain. Okay, we want this, and then we also want the radiating outward. So we also want no reflection from the signal in the smaller domain, right? We will still have a boundary. Your model will know that there's a boundary because there's some differences at the boundary, right? So we want to receive the signal and at the same time avoid the reflection from our own signal. Without reflection. Okay, so I'll draw a schematic diagram. So input of signal, no reflection. Okay, so how do we do that? Again, we are using the same example. This is time. The same example as the last slide. Okay, here E is coming from the left-hand side. And D is coming from the right-hand side. Okay, E, D. So we know the information from larger domain. So this side is larger domain. This side is smaller domain. The information from larger domain, right boundary, DE. So this is just rewriting the values for D and E. But here is for the larger domain. Here we know that E the values for E at x equals to 0 would be equal to the larger domain. So it turns out that we have larger domain on the left-hand side also. Okay, so they're equal. So at this location, they're equal. So this is how you you are introducing the signal from the larger domain to the smaller domain. Okay. So the problem here is that if you apply this, here, this is L. If you apply it here, so U from the larger domain equals to U from the smaller domain. And if you do the same for eta, that will generate physical. That's not the way to do it, physical reflection. So the proper way to set the open boundary condition here is the same as the previous method. So at the right boundary, we set the new variables to be equal instead of U and eta. So U minus eta G over C. U, U E. Okay, we rather set these two equal, these equal instead of the original two variables. So we applied one wave equation at the right boundary. We do the same, right? This is what we found, right? We apply this to a certain variables to make it to allow the open boundary condition. Okay, so we apply this to the whole variable. This is E. And we do the same for the larger domain. And then do subtraction for these two. Then this is how we should introduce the large scale variable into the smaller scale. Larger scale information, which is this one, should be imposed like this. Okay. Okay, so now you know that at the boundary you can apply the boundary condition. You can apply the this. So this is not constant anymore, right? You have tried constant. You have tried different things last time, but this is another method, which is the open boundary condition. Will reduce the reflection from these two, or reduce the incoming signal from these two locations, from the boundaries here. by doing this, applying, so this is like an operator applying this to a variable, then you will not get the reflection from that variable. So if you want to introduce the outside world signal at the same time, so this is what we do. So we still apply this operator, but it will be the difference between the inner world and the outside world. Okay. Okay, so actually it's not very, if you have no questions, then I'll go forward. Actually, it's not that useful in the practical world, in the research world even. Things that are too theoretical and not very applicable in earth science actually. Most of the times we do this instead, we do the sponge layer. So for the sponge layer, this is the region that you are interested in. So you want to do, this is actually applicable in all other geophysical modeling, I guess. So this is the domain that, the spatial domain that you're interested in. And you will spend a lot of other computer resources on the boundary surrounding the domain. So this layer is what we call the sponge layer. So whatever the signal we have going through this wall, the hope is to have this layer to absorb all the signal. And you will make this boundary as smooth as possible. So whenever your signal is going through this wall, it will not think of it as a boundary. It will think of it as another domain. Okay, but here actually it is an absorbing layer. So the points here are wasted. You will never look at the results coming from the sponge layer, because it's the main purpose of this layer is to reduce the signal to 0. Okay, and this is another boundary, right? Another boundary, and your signal, when it goes through this boundary, the energy will be dissipated inside the sponge layer, and eventually and hopefully it will be 0, touching the actual boundary of your model. And this is one of the ways. There are many, many ways. We have, I don't know, my FYP students found that this is not very useful, actually, but this is coming from the textbook, so I'm introducing this for you. So we add another term, and it will be depending on the distance from this boundary. So if it's further away, then you will reduce more signal. If it's close to this one, you don't want to reduce as much, because if any sudden changes to happening at the boundary, your model will see that as a boundary, an actual boundary. So we want the signal to go smoothly into the sponge layer and then dissipate it there. So it will be a function of distance between these two walls. Okay, and this is actually the common practice in simulating abstract condition, actually. So, or any geophysical fluid simulation. Okay. So the following part should be pretty straightforward. I just want to give you a little bit of the idea of how we look at the problem, look at the boundary problem. So here is an example coming from the textbook. So the values here are showing you the error. So what would be so-called error? It's so-called error. It's not actually, I don't think it's actually error. It's just coming from the differences between the two simulations. So the first one is that you have only one domain with the 2.5 degree resolution. Delta X is 2.5 degree. And this is high resolution, right? So if you want to somehow, if you want to reduce the computer resources you want to spend in this simulation, you want to do the outer world with lower resolution, and then the domain of interest with high resolution, the original resolution. So, and then you think that, okay, they should give you the same results, but actually it's not that simple. Okay, if you do subtraction, you will see some boundary effect. Okay, so this is the inner zone, the dashed line here, the inner zone. And you can see that if you suddenly have a boundary here, they are different. Okay, they're giving you different values, which means that anything you see here may be coming from the boundary. Okay, and then this is especially serious in the locations where you have a lot of synoptic disturbances. Okay, so be careful with the boundaries that you set. Don't set your boundary at the location where a lot of things are happening. Okay, here it's also another situations for different 1, 2, 4, 8, 16 are the different domains in here. Of course, 16 should be the best one because it's the largest one with the same resolution. If it is with the same resolution, then it should be the better one. So this is the root mean square error. 16 is smaller, and if you compare the results, then you can see that it's not able to simulate things happening at the boundary, of course, because it is the boundary, and you have some special effects happening. And for 16, it's able to simulate some smaller features. Okay, so they're both showing the domain in here, but this is coming from simulation 16. Okay, you will have to do exercise 3 this week. For the lecture 8 is not that long, and I think, and then we only have 1 question, so I think you can handle that. So 2 questions this week also. Okay, let's take a break for 5 minutes. Okay, let's make it 12:30. Let's come back at 12:30. Any questions? Any questions with the handwritten notes? Okay, let's start the lecture 8. So this time is this lecture is kind of relaxing. We only have 1 question, and the content is not as hard as the lecture 7. Actually, lecture 7 is the most difficult one, actually. So in this lecture, we are going to talk a little bit about the subgrid-scale processes. So what does it mean by subgrid? So here is an example. If you have a model simulation with horizontal resolution of 50 kilometers wide. So delta X here is 50 kilometers. So why do we use, so we have a lot of computer resources these days. Why do we use a resolution that is so low in here? So because this one is large enough for you to use hydrostatic balance, actually. So, but this is like the outside topic. So if you have this resolution and you have different clouds here. So for example, you have a very, very large clouds. The size of it is around 100 kilometers wide. And of course, you can use different grid points. So it can be represented by the different grid points. because it's larger than your resolution. Right? Remember last time we talked about the size that can be represented in a model. Okay, so what if you have smaller clouds like this? So each of them is just 5 kilometers wide. Okay, what would you do? So we need to use other methods to guess what happens within a grid. For example, this grid. So if this is the region for this grid, then you will need to gather the information for all the clouds. And then even though you have like 10 clouds in here, 10 cloud clusters in here, you will have to reduce the information into one single value or a few values, and they are representing the properties at this red dot here. Okay, so you're kind of relating information around the grid with the information on this dot. Okay, so clouds cannot be explicitly represented if delta x is 50 kilometers, and they have to be parameterized by parameterize or parameterization is to relate the things, individual things happening in the subgrid scale. So in the one side, inside one grid, okay, there are different things happening. For example, there are different clouds, and then we statistically or use some algorithm relating the properties in here with one or a few more cloud index or indices. Okay, so this is one of the examples. We relate the things, a lot of different things, individual things happening with the information on this dot, which is the, for example, cloud index. Okay, and changes in this index will represent changes in the cloud total size. So you are kind of reducing the information, reducing the dimension of the data, or reducing the size of the data. So because there are a lot of them, and you reduce them to a certain index. For example, if this index is larger, then you know that there are more clouds in here, or smaller, than fewer clouds in here, right? So just very same idea as doing statistical modeling. So you have some data, and then your data will be these bars, right? So statistically, you can fit a curve in here, and you can just represent this curve by a few values, right? For example, the mean and the standard deviation, and then you have the shape of the whole curve. You reduce the information to these two, and then you will use that to do some other analysis, right? Maybe fill in the information in this hole, okay, things like that. And for in the current situation, we reduce the information, for example, different cloud properties from different clouds, and then we do dimension reduction. So we reduce the information. Maybe we find the highest one, or maybe we find the average, and then to use that to represent the whole grid. Okay, and then we come up with an index. And then why do we care about this? Why do we reduce all the information to this dot? Because the information here will affect other variables. For example, if you have a lot of clouds, maybe you will have to deal with the reflection from the solar radiation, right? You will have other effects in other parts of the Earth system. Okay, so there are different reasons. So even if you have the most powerful computer in the world, you will never simulate the space in a continuous way, right? Okay, unless you have the analytical solution for the Navier-Stokes equation, then we don't need to do simulation anymore. So the limitations are actually closure problems. So why does it call a closure problem? If you have, okay, for example, if you have a system of equations, you have 3 equations and you have 3 unknowns, then you can solve the equation, right? But here you have infinite number of unknowns. You have a lot of unknowns. There are a lot of things that you don't know, but you only have a finite number of governing equations. So the set of equations is underdetermined. So you have more unknowns than the number of equations. Then there should be some cutoff. Okay. For this discrete representation, so we have the 7 primitive equations. We have introduced that, right? Already momentum equations, continuity, and heat, and the first law of thermodynamics, things like that. Okay, we have 7 primitive equations, and they're explicitly calculated for the orange dots in here, and also for the smaller scales. For each of the small scale, you will have you have your own primitive equations, and it's just too computationally expensive to represent a process directly in smaller scales. So we will have to do some cutoff. Okay, so there are scales that you cannot deal with. Okay, we have talked about the first point, and the second point is that we don't have enough information. We don't have enough knowledge about the natural world. So there are a lot of processes that we don't know. Okay, so that's the place where we have a knowledge gap. Okay, for example, if you have the 7 primitive equations, also other known processes, and then we have the unknown processes, the mechanisms that we don't know. For example, recently people found that there are some large holes in the Siberia region, and they found that it was the explosion from the methane underground, and not until the explosions people didn't really care about that, and that's one of the processes in the environment. Okay, so this is an example showing you why we will never be able to represent all the processes within the system. So the example here is cloud formation. So first of all, we start with a very, very simple model with one component only, with only air. There's no water in the air. Okay, and then you think that that's not enough, right? You want to have representation of water suspended in the air, right? So you separate the representation into 2 parts, the dry part and the water vapor. Okay, so 2 component system. And then you think that, okay, that's not good enough, because water vapor is not just water vapor in the atmosphere. We have water droplets, we have ice form, so the 3 phases, we have the 3 phases. Okay, and then we will making your model further complicated because we have many component system here. So for each of them, they should have their own balanced equations. And that should include processes of sources and sinks. For each of the phases, of course, they are changing from each other constantly in the atmosphere. Okay, and then you found that that's not good enough, because if you want to talk about the change of phases, you will need to talk about the growth of cloud. When you're talking about cloud formation, the growth of cloud and the different processes, very small scale processes. For example, how the cloud droplets grow. This is how they grow. Sometimes if you have falling droplet, very heavy one, and then they're bumping the smaller droplets in the air, and then this is how you have larger water droplets or raindrops in the atmosphere. Okay, and the growth is not linear over time, so they're very much complicated. Okay, also we have talked about the second point. So also the third point is that we have incomplete representation at the interfaces. So the interfaces are very hard to simulate because, as you already know, the boundary conditions are very hard to handle. And also we need to have all the information we have. We have all the information the exchange of momentum, heat, moisture, or mass exchange between the domains. And some fluxes are missing. So there is a need to do parameterization because of the limitations. So the goal here, the parameterizations, is to do an educated guess. So it's all about guessing. So how do we guess? How do we make a logical guess? So here we have some grid point information, right? Large scale circulations. So the grid points, they are most of the times representing the large scale or the average values. So if we separate any parameter into two components, the first one should be the mean, which is also the large scale circulations, and also the perturbations from the mean, okay, the U prime here, which is representing the smaller scales, more varying a lot more comparing to the mean, okay. The smaller scale, any. So for the course 4210, we study the boundary layer. Actually, the spirit behind this boundary layer actually is about parameterization. Everything you study in that course is parameterization. So this is how we parameterize. So we parameterize the flux, the momentum flux in the smaller scale with the grid scale information, the large scale. So the shear in the large scale will generate flux. So this makes sense, right? If you have shear in the atmosphere, then you will have smaller scale twirling wind, right? So this is the idea. It's not, I would say it's not exact physics that you studied. So everything proving from the very, very basics. It's all about observation and also about this educated guess. So how do we match this educated guess with the observation? We can never study earth science without the observations, right? Okay, so the 7 equations that you study, most of the times we call that the dynamical core of your model. They only deal with the physics or thermodynamics in the model, and there are different things happening in the Earth system that you need to use the subgrid-scale processes. You need to use the parameterization. For example, the cloud processes or boundary layer processes we study, and radiative transfer is very important. So that's how we get the energy from the sun, right? And also hydrological processes. And also we need to deal with the interface with other parts of the Earth. Okay, so there are different processes that we need to do parameterization. We have talked about this in microphysics processes, and also radiation. We will talk about this a little bit in the next part. Convective, also we'll talk about this in the next part. Boundary layer, we have done this with the course. I'm not going into the details. So the soil, vegetation, atmosphere processes, I think Amos is working on this, is the expert. I'm also not talking about this. Also this drag. So by drag, you're talking about friction. And by friction, you're talking about nonlinear things happening. So nonlinear things is very complicated, right? So that's why we need to do parameterization also. Okay, again, this is again an example showing you how we can relate the information of the resolved scale, the red dot, with the subgrid scale information. So subgrid scale, so in the resolved scale, if it's the relative humidity is very, very high, then you will have condensation in the subgrid scale. So in the small scale, and then your parameterization will decide if we have cloud forms or latent heat releases. And then this will be feeding back to your grid scale other parameters, for example, temperature. Okay, so that's why we need to care about subgrid scale processes, because it affects the larger scale. Okay, we need to know the rationale behind the schemes. Why? Because there are a lot of different schemes. They all have sound. Physics. So each of them may be applicable to different situations. So you need to be careful. So here we will talk about the cloud microphysics. So it's all about studying the so-called particles, different species, different water species of in the atmosphere. So you have different species here. The cloud droplets, they have this size, 0.0 something millimeters, and we have the ice form. For the ice form, we also have different forms. Maybe snowflakes, maybe mixture of water droplets with the rim ice particles. So it's called rimming. So it's a mixture. So that's why the whole thing, the whole rainfall or precipitation thing here, or the water in the atmosphere thing here, it's very complicated, because the three phases, they're changing to each other constantly, and they are a mixture of them, and they appear with different shapes and sizes, right? Smaller ones, they have different names. Larger one, hail and grapple, and they all play a role in the abstract simulation. So the goal here is to describe the cloud particles and predict the changes occurring in the microphysical processes. So why do we do this? Because we need to have correct modeling of the precipitation. So you can see that if you don't have the right microphysics, then you get different forms of precipitation due to different situations. So that's why if you have if you have a bad microphysics parameterization scheme, then there will be inaccurate modeling. And that would in turn affect the simulation results greatly, because one of the biggest uncertainties in climate modeling is clouds. Okay, if you don't have the right representation of clouds in your model, then it will affect the radiative forcing. It will affect the thermodynamic feedback, because it provides latent heat for the dynamics. Okay, it will also, which means that will affect your circulation also, because the heating changes, right? So that's why these schemes are very important. If you don't have the right cloud microphysics scheme, then you cannot properly represent the thunderstorm happening a lot in the tropical region, for example, because if your water droplets, if your water is going up through the 0-degree level, then you will have ice. So that's how thunderstorm happens. So there will be the ice will be rubbing each other, and there will be a mixture of ice and water circling around above the 0, depending on how strong your convection is. And also that would affect the precipitation later. So that's why it's important. Okay, so this is showing you how complicated the whole thing is. So that's why we need parameterization to simplify everything. Okay, I'm not going through into the details here. So this is basically how we deal with the different species. For example, if you have some liquid, if you have some ice column, ice plate, different species, we need to have different definitions first. And for each of them, for example, for liquid, you separate the information into, for example, different masses. Okay, so and the distribution of them. So the goal here, so there are the first category of parameterization here is to simulate the changes for this distribution. Okay. I think this is the same for air quality study. If you want to study suspended particles, PM, in the atmosphere. So this is how we do this, or dust. So it's same as studying dust. So you have different sizes. And if you collect the sample from the environment, from different sites, you will get different distribution. So that's how we study the changes in the atmosphere or in the environment. Okay. And I'm not going into details for the second one. Okay. Convection. How do we do parameterization or convection? So before we talk about that, a little bit about convection. So convection is just overturning of your fluid due to the different densities in here. And I've already talked about this, so it's very important to have the right representation for clouds in the atmosphere due to the different effects. And the radiative forcing for shallow cumulus clouds here is very important because if you probably already know that the higher clouds and the lower clouds, they have different rates of reflecting the solar radiation and re-radiating the long wave radiation back to the space, right? If for lower clouds, because they are radiating at a higher temperature, so that's why they are more effective to radiate the heat back to the space, which means that they help reduce the global warming problem. Okay, so that's why it's very important to do this, to do the simulation. So there are different types of convection. For example, the ITCZ intertropical convergence zone. Also for the Walker circulation, which is involved in the El Niño southern oscillation. So so why do we care about the convection? Because so this is a graph showing you the Pacific situation, the situation happening in the Pacific, a lower level wind, of course. So we have the trade wind coming from the easterly trade wind, and then they converge at this ITCZ intertropical convergence zone. And normally you expect a lot of rainfall, right, around this zone. And then there's a place which is very specific for our Western Pacific region, because there's a place where you have the monsoon trough, which is like you can see the wind is turning direction when it's crossed the equator, because the Coriolis effect, obviously. And the westerly here, I think it's very special around the world, because you will not find a lot of region where you have westerly in the tropical region, right? And then we have the convergence. The monsoon trough is talking about the convergence here with the trade wind, and that's why we have a lot of tropical cyclones in here. So why do we care about the convection? Because the convection will lead to moist convective processes here, a lot of thunderstorm and tropical cyclones, things like that, and that would affect the large-scale processes. And the large-scale processes, which are these arrows here, the wind, will affect the moist convective processes. So large scales is talking about the convergence, and then this one is talking about the rising motion and the condensation and then rainfall, right? And then that would affect the large-scale processes. And we need parameterizations for this. Why? Because it's also involving very small scale stuff. Of course, you look at this graph, it's very large scale, right? But actually it's the condensation of, it's starting from the condensation of the very small scale water droplets. So when you're relating things when you're relating things this large with the things so small, then you need parameterization. Okay, convective parameterization. So relative humidity. So here is giving you a question. So you want to decide the relative humidity for this grid point, and you know that there are locations where you have different. Okay, this is just an example. If you have measurement like this, then you know that, okay, it might be raining later, right? It might rain later, but how do you decide if it rains or not? Because not the whole grid is 100%. So the goal here, the goal of your parameterization is to active moist convection at an relative humidity lower than water vapor saturation at the grid point. So it shouldn't reach 100% to rain in your model world. If that is the case, then you will never get rainfall, right? So that's not what we want. So the goal is to do this and to generate grid box value of convection, and then that convection will define the effects of convection on other grid scale variables. So this is also talking about the effect on other variables. Okay, why do we talk about condensation? Because it's about the it's about convection and how it leads to moist convection processes. Okay, so this is like a revision. I guess you already know about this. So if you are, this is a graph showing you the saturation vapor pressure, right? Y-axis, and x-axis is the temperature. So which means that this depends on temperature. So how much your air can contain water. So this is deciding the maximum pressure of the water vapor, which is the maximum amount, which is talking about the maximum amount of water that your air can contain. And it depends on the temperature. So the higher the temperature, the higher this water vapor saturation pressure. Okay. And let's say if you're here, if you are at a certain temperature, and if you have a certain water vapor, so you can think of it as the amount of water vapor, a certain amount, and it's not saturated yet. Okay, so there are two pathways suggested here. The first one is that you reduce your temperature to a certain value. If you reduce your temperature to a certain lower temperature, then you have condensation. So which means that this is the dew point temperature, right? And your water vapor, this is the first pathway. So your water vapor content is the same. Okay, there's no addition of water vapor. It's just that you reduce the temperature so that your water vapor will condense. Or the second pathway, you add the amount of water vapor, right? If you go up in this graph, you're adding the amount of water vapor and you stays the same temperature. Okay, two pathways. So you add a lot more water vapor in your domain, okay, with the same temperature. Okay, or you can do both, right? Okay, so this is what we call a school T log P diagram. Don't worry, people invent this to avoid the math. Okay, so the complicated thing here is to interpret, or it is to navigate yourself through the different lines here. So first of all, it's still a PV diagram. So P in the vertical dimension, PT diagram, sorry, PT. So this is temperature, but it's a school T diagram. So the temperature here, so this solid green line is temperature 20 degrees Celsius, temperature 0 degrees Celsius. Why do we use school temperature? Because your air will no longer be the same temperature when it goes up, so it doesn't matter if it's school or not. Okay, so 20 degree minus 20 degrees Celsius, which is this solid green line. Okay, and of course the the p dimension is in log scale. Okay, so isobars are in the horizontal way, and then isotherms, same temperature, schooled. Okay, and there are also other variables here, other lines here. Maybe I will talk about that with this example. So let's say you have some measurement at the surface, T equals to 40 degrees Celsius. And also you have measured the water content of your air parcel. It's 2 grams of water per kilogram of air. Okay, so this is the mixing ratio representing the moisture content. Okay, moisture content, temperature, and your temperature at the surface will go up along a certain line, which is the diabatic, the adiabatic, dry adiabatic. So we assume that your air parcel doesn't have any exchange with the environment, so it's going up with the dry adiabatic situation. So the dry adiabatic lines are the red lines here. So very simple, we just go along until you hit the point from the other side. Okay, in here, your water vapor content is not changing because there's no rainfall, right? So your water vapor content 2 here, 2 grams per kilogram. So it's going up nicely without any loss. And then they reach. Okay, when they reach, there would be condensation because your temperature is decreasing so much. This is 40 degrees Celsius. When you go up with the dry adiabatic situation, then your temperature is decreasing, right? This is 20, this is 0 degrees Celsius. The temperature is decreasing as you progress up into the atmosphere. Okay, and they meet, and this is the level where you have condensate, starts to have condensation. That's why it's called cloud base. And then after that, it's just moving along with the moist adiabatic, which is the dash red line. So it's kind of between this dash red line and this one. So that's why it's just, you just draw it with bare hands. Okay, don't worry, people used to do that in the past because they didn't have computer. So these levels are the levels where you have the condensation. That's why theta is no longer constant and the lapse rate is different, right? For the dry rising motion, the lapse rate is 10 degrees Celsius per 1000, and for the moist adiabatic process, the lapse rate is much smaller because of the presence of moisture. Okay, why do we talk about this? This is not for this course, actually. It's not numerical methods, it's not modeling, actually, but this is how we do parametrization. Okay, so the kind of like a small question here, what is the dew point of the air temperature? So you just use this and then find out the degree. What is, it's around, this is 20, it's around -7. Okay, so the dew point temperature at the surface is -7. So it fits nicely. If you found the moisture content, you will find the dew point temperature, or if you have the dew point temperature, you will find the moisture content. Okay, so next we need to deal with the convective available potential energy. So it's very fancy, this term, but actually it's just the ratio between the temperature of your air parcel, or the difference between the temperature of the air parcel and temperature of the environment. So we do subtraction. Theta is the temperature of the air parcel minus the environment and divided by the environment. Okay, so if you have an air parcel warmer than the environment, you have positive CAPE. If you have air parcel temperature lower, so this is cooler than the environment, you have negative CAPE. So it's as simple as that. So how do we do measurements for this? We use the weather balloon. I think we have 2 releases each day in Hong Kong. Okay. So pretty simple. So if you do, so there are two lines in here. The first line is the line where you start from the surface like this, go along the dry diabetic, and then go along the moist adiabatic. So this is the red line we talk about for your air parcel. So you're talking about anything happening, okay, anything happening at the surface. So it's all surface driven by the data in the surface. So it doesn't matter what's happening in the upper levels. So if this is 40 degrees, this will be the pathway your air parcel will go through, which is the yellow line here. And then you have another line. This line is the measurement from the weather balloon. It's in situ measurement, the measurement at the locations at different heights. This one is just your own analysis, right? Driven from the surface. Okay, and there will be differences. The differences, you can use this equation to find out if you have positive energy or negative potential energy. Okay, of course, this one is positive, right? Theta. The temperature of your air parcel is higher than the environment. If it's higher, then it will go up, right? It will go up indefinitely because there's no resistance. Okay, this positive Cape area. Okay, that's why you can see that there will be, this is the cloud base, the lifting, the level of the lifting condensation level. Lifting condensation level. Oh, okay, never mind. So the level of free convection in here. So there are different situations. I'm showing you different school TLP diagram. So this is how we do analysis starting from the surface. We have talked about this 2 slides ago. So this one is coming from the water content and this one is coming from the temperature, and they meet somewhere. This is the place where you start to have condensation, lifting condensation level. Okay, and then your air parcel will go through the atmosphere with moist adiabatic condition. Okay, between this green line and this green line, 335 and 386. So they just draw it. No, it's not very accurate, but this is, remember this is drawn by hands a few decades ago. Okay, and people do this. So this is moist adiabatic situation. If your line is crossing with the environment, this is the line where you have level of free convection, because this is the location, or this is the level where you start to have positive Cape, right? This region is the region where you have your air parcel is warmer than the environment. Okay, of course you have a negative region in here, which means that your air parcel has to overcome this negative Cape levels to reach the positive Cape level. Okay, this is a situation where the two are very close, the two levels are very close. Why? Because if you compare this with the first diagram, if you compare this with the first diagram, you have much warmer surface here, right? That's why your negative Cape region is also smaller. So this one is probably more active. This one has more active convection. Okay, this is the region where you have negative Cape. So this layer is kind of special. It's called inversion. So you have increasing temperature with height. So this is acting as a capping lead to your atmosphere. This is the situation where you have very bad air quality because the air cannot go to the higher levels and disperse. Okay, so your air parcel has to overcome this negative Cape region in order to reach this positive Cape region for the free convection. Okay, I think I've already explained this, so I'm not going into the details. Okay, so this is also less important in this course actually. Different types of clouds. The important thing or the take-home message here is the formation mechanism of different clouds. So this one is, of course, from the convection, right? It's going up. It has a vertical structure, and these two you can see that horizontal structure because when they appear, the atmosphere is very stratified. So there might be some very stable situation here. For example, the inversion, and your convection cannot go through this layer. So that's why the clouds are limited to a certain layer. Why do I talk about that? Because there are different types of convective schemes. So there are deep layer control schemes where you look at the situation for the whole layer, large scale stability, or just the low level control convective schemes. Just look at the lower level condition if it's good enough for large scale convection. I'm not going into the details for this. So this is an example, one of the convective parameterizations, Max-Miller scheme. So you have learned that you can do this intersection, right? Starting from so for the dew point temperature or the mixing ratio on the left-hand side. So this is the profile, and on the right-hand side of temperature profile. And then you can draw the intersection. So normally we just draw the intersection for the lowest level. But here, what they found is that they do this all the way with the two profiles in here. And then we have a mixing line. Okay, so this mixing line is actually, we have some characteristic mixing lines for different situations. And there are ways to calculate this mixing lines, not by doing this, okay? So this is theoretically, we can find this line, but people have found different methods to find this line. So what they do is that they have measurements, two profiles, and then they have a mixing line, and then they use this mixing line to do the reverse back. This mixing line is calculated by your scheme. Reverse back, not this mixing line, okay, the other mixing line is calculated by your scheme, and then you do the reverse. Okay, we'll not go into the details, but I'm telling you the rationale behind this. So the mixing line is depending on different things in your model, and they calculate that and do the reverse and then find the new profiles for your dew point temperature and for your temperature. Okay, the two profiles in here. So the newer profiles, your model will assume that your atmosphere will adjust to this newer profiles, which means that there is room for moistening of your atmosphere if you move to your new profile, and also there's room for warming in your atmosphere. So your scheme will decide how long it takes for your model to adjust to your new profiles, and then rainfall would happen because of this. So that's why I am telling you how to read this graph. Okay, it's less important in this course, but for all the students studying atmospheric science, you should know about this good T log P diagram. So the assumption here is that the atmosphere will be forced to adjust to the adjusted profiles, the black thick lines in here, adjusted profiles in adjustment time scale. Okay, maybe we can take a break right now. Take a break for 5 minutes. Okay, maybe a little bit longer. Maybe we can come back at 1:25. Okay. Any questions? Okay. Okay. Let's continue to talk about radiation schemes. Right, before we talk about the schemes, just a little bit background for the radiation in the atmosphere. So that's how we get the solar radiation actually. Solar radiation reaching the Earth's surface. A part of it is reflected, and a large part of it is absorbed by the surface and absorbed by the atmosphere. So we need to study this part because it's absorbed by the atmosphere. And it's not that simple. The process involves different layers of atmosphere, and they all have different properties. And this is just a revision for you. So the spectrum of the shortwave radiation coming from the Earth and coming from the sun, and long wave radiation coming from the Earth. So all the energy exchange are handled by the radiation component in the model, except for a few things. For example, convection, conduction. This is handled by the boundary layer and parameterization, of course, because of the turbulent fluxes, and also the latent heat release, handled by the precipitation processes, and also the evaporation handled by the land surface component. So different, if you look at the details of a model, so different processes, they belong to different schemes or different parts of the model. Of course, other things happening here, they are handled by the radiation component. So this is just also a revision. So we have an unevenly distributed amounts of radiation over the Earth. So that's why it's important to study that, because it is the actual forcing of the different things happening in the atmosphere because of the differential heating due to the radiation. Okay, so the radiation parameterization, the goal for it is to provide a fast and accurate method to determine the total radiative flux and its vertical divergence. So why do we need to decide the vertical divergence? So this is the flux, the downward flux and the upward flux. And the difference between them, of course, is the total flux, right? Total downward or upward flux, the net flux, okay? And we want to see if it has divergence in the vertical sense, which means that if it is accumulating in the atmosphere. If it is accumulating, then your divergence term here could be positive or negative. Okay, if it's accumulating, then it would change the temperature, right? So the aim here is to find the ways. So this is the effect and why we need to study the radiation. Okay, so the aim is to find the ways to calculate upward flux and downward flux efficiently and accurately. Okay, for example, if you are looking at this layer, then if there is changing, so if you do subtraction and then if there is changing of this subtracted results over height, then you have some accumulation or some convergence or divergence of your flux, and then you will change the temperature of this layer, whether increasing or decreasing the temperature of this layer. So this is why we call this, sometimes we call of radiative cooling. So that's how we achieve that. So we need to simplify things here. The practical simplification is to do simplification for the long wave and short wave radiation spectra. And it's very easy to separate them because they are two very distinct spectra. And the absorptions here, we need to simplify them. Maybe we can fit a curve here, right? Associated with specific wavelength bands. And we need to, of course, we need to separate the calculations into two categories long wave, short wave, and for different wavelengths, upward and downward. Okay, so let's say if you want to look at the change of your radiative intensity, I here, for a certain wavelength. Okay, we just take out one wavelength here, or wave number, okay, one of them, and then we look at the effect of that radiation, okay? So the change of your radiative density would be due to, of course, your original intensity, okay? And also or your density of the material and also thickness. So the thicker your layer is, so your radiation coming from the left-hand side, and then it goes through this material and then going out, okay? And the longer the distance is, the larger the change in the radiative intensity, okay? And also absorption coefficient. So this is due to the material inside this layer, okay? And very simple. Simple demonstration for you. Radiative transfer. Okay, we call this the optical depth. Wavelength length. Oh, so at a certain thickness, your intensity of the radiation. So this is how we arrive at the equation here. So the intensity is actually the reduced version of the intensity entering the layer, and it's reduced according to your optical depth or thickness. Okay, reduced exponentially here. So, and then we integrate this radiative intensity over all wavelengths, because this is just for one wavelength. We get the radiative flux density. Okay, so the next step is that, okay, now we have the formula for the radiative intensity here. So for different distance, okay. Then we can work around this radiative intensity to do the parametrization. So the first very simple parametrization is the first kind here is what we call the bulk expressions for gaseous absorption or clouds. So here we need to do a few measurements. For example, the temperature, the 2-meter air temperature, putting back to this TA, and then we use this prescribed relationship. Okay. So this relationship is for the upward radiative flux density. So when you have the 2-meter air temperature, you can find the relationship here. And then, of course, you substitute that back. And then you calculate the radiance in here. Okay, if you have found that this is the upward radiative flux density from the surface, and then this one you also substitute this, the 2 meter temperature. And then we found the downward radiative flux density of course, it's coming from the atmosphere, right? Long wave radiation from clear sky. So where there's no clouds, your atmosphere will still absorb the energy from the short wave and then we radiate back, right? Some part of it is downward. So you do the measurement for this, and then you will have the difference, right? You can use the difference to calculate if it's changing over height and if it would lead to increasing or decreasing of temperature. So this is one type of parameterization, which is a kind of a very economic way to do that. Okay, and the second stream is looking like this. Okay, please don't be afraid. This is just optional. So I'm going to say a few words only. If you don't understand, it's fine. So the goal here is to do integration for your the change of your, so you have to change, right? You have to change of your radiative intensity. This is like a simplified version, okay, here for just one wavelength. Okay, so normally if you integrate this over the whole atmosphere, you can get the upward flux or downward flux density. So here, this is just very similar to what we are seeing here. Okay, this one. So the intensity entering the layer, the original intensity, and then the reducing term. So this part is supposed to be reducing your entering intensity, right? So it's very similar. So here you have the emission from the surface, which is the original intensity entering the atmosphere. And then we have the diffuse transmission function. So this is representing the reducing part, the attenuation from the surface, okay? And then we need to integrate the whole thing over different frequency or wavelength, okay? As simple as that. So original intensity, attenuation, and the integration, okay? It's basically the same for all the things in here. So this one is emission coming from the surface C equals to 0 from the surface. So that's why it looks kind of simple, okay? And for the second part is the emissions from each level. So from each level, you will have the original intensity, and then from each level, you have the attenuation from, of course, from each level, okay? And then we need to integrate because from each level, it will have its own intensity and its own emission and its own attenuation, and we need to integrate that first, okay? So the integration, the first integration here is for different levels, and then the second one again is the same as this one. So integrate for the over all frequencies, as simple as that. So upward, it's a little bit complicated from the surface and from different levels. And then downward, it's basically very similar to what we have just talked about. So from different levels and different densities, right? So similar to the second term in here. And then we need to, okay, so if we want to go into the details of this, so of course you don't want to go into the details of this. No one wants to go into the details of this. So if you want to study this, you have to go further because the attenuation term is kind of complicated here, the attenuation, and it depends on the incident angle, okay? The incident angle. So diffuse transmission function is the attenuation. I don't want to go into the. Okay, so it actually depends on the absorption coefficient in here for each of the gas. So that's why, okay, now you have some ideas of how complicated radiation parameterization is. That's why it's very expensive in any kind of atmospheric model. Okay, when I was a graduate student, I just ignore this and then choose one of the schemes, and that's it. And nobody actually really care about that, unless you're dealing with some wrong convections or things like that in the atmosphere. So here we try to involve the absorption coefficient in the attenuation, because the attenuation is due to the absorption, right? So absorption coefficient. And also we need to take care of the angle, because we need to integrate the whole angle, all the angles. But this is where the parameterization is happening. We are not doing the integration of all zenith angles, and we just replace this integration with a certain parameter. So this is parameterization, simplifying things. Okay, I'm skipping the second one. Okay, so this is just telling you the two-stream method we have just talked about. Integrate over all frequencies, because for the different frequencies, they have different behavior. We have talked about this, the spectrum, and then the absorption coefficient for different types of gases. Okay. So the limitations for parameterizations is that they are actually developed from statistics or experience. And in other words, they're not based from some physical theory, but we need them because we don't have the perfect tool. The tools we have are probabilistic. The reality is deterministic, right? So we don't have the perfect tools, and we need to use parameterization. Even though, okay, some people would tell you that, okay, I have a very powerful model, very powerful computer. Even that, they need parameterizations. Whether you need to use more or less, that is another question. Okay, so their performance depends on scales. So it's not like you can use any scales for all the situations. It's not like you can use just one scheme for all the situations. It shouldn't be like that, because different schemes, they handle different scales. And for example, some convective parameterizations perform better in mid-latitudes and some better in the tropics. Okay, and global models, of course, some global models, they use lower resolution. Coarser grid, they use one convective scheme, so they are not able to choose the schemes best suit for each area. And another thing about parameterization or resolutions, the problem of resolutions is that there is a resolution where there's a place called no man's land. So you have some explicitly soft scales here with the radiation resolved convection, and you also have the parameterizations, and they should meet somewhere, right? But they should, in some sense, you think that, okay, they should meet, but actually they shouldn't meet, right? If they could meet, then what happened in that scale? Okay, so there is a scale where the two sides in here, they don't meet. Okay, so the scales here are not represented, they're not simulated in your model, which is not good. Okay. Okay, I think we only have one very, very simple exercise this week. And also you have to do the last question for the last week. And then you can hand that in, submit that after the midterm, before the next lecture. Okay. Any questions? 冇問題。Okay, also 7.2 one-wave equation. I thought they have already done this. Okay. 即係上個星期就係做咗呢條，係咪？
上個星期就係做咗 exercise 1同埋 exercise 2嘅 method 2同埋 method 5嘅，因為上個禮拜個 one wave equation 係未夾嘅。
哦 ，OK， 好，咁呢度做呢題。OK， if you have no questions, then you can leave the classroom. Thank you.